You look very summery.
Yeah, well, it's summer.
Is it hot in Berlin?
It's not too hot, but I came from the gym, so uh, I still feel very hot.
Nice. I also have my summer clothes on. All right, cool. So it's working. Then I wish you a good lecture, guys. And yeah, I'll see you around then.
Yeah, thanks. Mm, okay. Um, I'll just connect with the tablet. Okay, so last time we finished the proof of Abel-Jacobi theorem, which is probably the biggest result we proved so far, and it will be maybe only secondary to the well pairing theorem. And the next thing I want to talk about today is isogenies. Basically, what we want, and this is compatible with the things we did for groups and fields. We want to have a notion of a map between two elliptic curves. I mean, so far we always fixed an elliptic curve, and we studied properties of this curve. But in general, if you want to understand an object in mathematics, you need to have a good notion of what it means to move between two objects of these types. So we have a notion of a rational function. Rational function called a rational function it can be viewed as a map function from the k rational points of E into the projective line. And if you think of it, the projective line is just another type of a curve, right? I mean, it's a one-dimensional algebraic object, and we can use this notion of rational functions to, well, I mean, of course, the key point of a rational function, it's a map defined by quotients of polynomials. Of polynomials on E. And in general, in algebraic geometry, I mean, we always want to talk about either of polynomials or quotients of polynomials. And I think this should be enough of a motivation to the following definition. So let E A B be an elliptic curve. So this is E over K. A rational map say rho is well is a pair rho being R comma S, where R and S are rational maps on E, and for all P in E, if I substitute P into S and R, and I treat S and R as the y coordinate and the x coordinate respectively, then I get that the equation of the elliptic curve is satisfied. That is, SP square is equal to RP cube plus ARP plus B. And here I just to make it completely clear, if P is the point at infinity, then I remind you, heuristically, we think of the point at infinity as being infinity comma infinity. So when I write this equation for the point at infinity, I really mean that S of O is equal to infinity if and only if R of O is equal to infinity. Okay, so this equation is you can just think of it as always valid for all points. When the point at infinity, you just substitute infinity in both coordinates. Okay, so this is a rational map as in contrast to a rational function, but it's not a standard terminology. I'm using it at the moment just to disambiguate the two notions, but in fact, what we, as I said, what we called rational functions before is just a rational map between the curve E and the curve of the projective line. Is this clear? Any questions about the definition? Lisa, what do you think?
Do I understand it correct that one can informally describe this map as substituting x and y that we had before for points for rational functions?
It's like I mean, we write the notation. Maybe it would clarify. We write rho from E to E. Right? It's because I give you a point xy on E. I mean on E of k, right? And rho maps it to a point of E of k again. And the way, I mean, if I want this property, so if P is a point on E of k, then rho of P by definition is R of P, S of P.
Oh, right. So we map a point on elliptic curve into a point on elliptic curve, and the rational function is exactly the map.
Yes, exactly.
Oh, yeah.
Yeah, sorry, go ahead.
No, then I think it's clear.
Okay. Now, what do you think?
Thanks, and this was helpful. So thanks, Lisa, for asking it. Then this means that if we had sorry another kind of like curve shape, the rational map would follow that. Equation too.
Yeah, let me generalize the definition to maybe help clarify the notion. I mean, more generally, suppose E over k is this y square equals x cubed plus ax plus b, and E prime over the same field k is y square equals x cubed plus a prime x plus b prime. Then a rational map rho from E to E prime is a pair rho equals r comma s where R and S are rational functions on E, and such that for all P in E, well, in E of K, let's say, RP square equals S, sorry, it should be S, SP square is equal to RP cube plus A prime RP plus B prime. And this really means that with the same convention for the point at infinity, I mean, the point at infinity says that R of O, basically R of O is infinity if and only if S of O is infinity. And what this notion gives you is for any P in E of K, I can apply the rational function rho on P. This really means that I apply the rational function R on P and the rational function S on P. And the equation here, star, this means that a rho of P is a point on E prime. Right? Because it satisfies, I mean, the X and Y coordinates of rho of P satisfy the equation of E prime. Is this helpful or no?
I think I'm digesting.
So let me try to explain it from another angle, I mean, or maybe just in other words. I mean, you can really start from saying that you want some notion of a map between E of K and E of K prime. Sorry, E prime of K, right? You have two curves, E and E prime. They are of this over the same field, but they have different coefficients for their equations, right? Yeah.
Quick question. Do they have the same order?
No,
or doesn't matter?
Not necessarily, no. You know nothing about, they're completely general.
Okay.
The only thing you know is that they are defined over the same field. Okay, so the coefficients A, B, and A prime, B prime are in the same field K. So if you want such a notion, I mean, of course, I mean, this is a set, this is another set. There could be many functions between this set, between these two sets. But we want functions that are defined by polynomials, or really quotients of polynomials. So, I mean, obviously, I need to give you at least, if I'm looking at the finite points, I mean, finite points have two coordinates, right? So if I want to give you a map rho that for any finite point P gives a finite point rho of p, then rho of p must be must have two coordinates. So I write it as r of p and s of p. Right? Whatever rho of p is, it has to have two coordinates. You follow or now?
Yes, thanks.
Okay, so, and moreover, if I want that rho of p would be a point in the target curve E prime, then the two coordinates of rho of p need to satisfy the equation of E prime. What does it mean? It means r of p. Sorry. I mean, so it means that I regard r of p as the x, s of p as the y, and I want that y square equals all the rest of it, right? So s of p square needs to be r of p cube. Well, what is written in star? Yeah. Okay, so this and for the point at infinity, I can say that I mean, it could be that S and R map the point at infinity to a finite element in the field. This could be. So I require this equation to be satisfied also for the point at infinity. And I mean, if I require this, I mean, of course, S of p, where p is the point at infinity, so S of O and R of O are defined. This when we talked about rational functions, we said that you can evaluate a rational function at the point at infinity, and you get something on the projective line. But the projective line is just a k together with an additional point. So I interpret this equation star. I mean, if R and S are, sorry, R of O and S of O are simply elements in the field K, then this equation star needs to be satisfied as it is. It's just an equation in K. And if I mean, if one of them is the I mean, if one of R of O or S of O is infinity, then satisfying this equation means that the other one must be infinity. Okay. Tell me what is missing now.
No, I think thanks, because it was very helpful. This, I think what it's like my head not wrapping around is the fact that you can have different orders on those curves, and then this mapping is like it not will always be 1-to-1, or
it will not always be 1-to-1, but as we will see, it will always be surjective.
Okay.
So this, I think your intuition is right, that you have a certain rigidity, but in general, also for maps of groups, right? I can map the group of integers to the group of integers modulo n by taking a to a modulo n. Right? This is not an injective map, but it's still a group map. So in general, maps between objects, I mean, for example, between groups, do not need to be injective. And remember that you always have the zero map, right? I can take any group G, take any group H. Let's say they are both abelian and written additively. You can map all X in G into the zero element in H. This is also a group homomorphism. So that's not a problem that something is not injective. We actually want to be able to move between two elliptic curves or two objects also non-injectively.
Okay, thanks.
Okay. Now, a main example. Let n be a positive integer. And the map bracket n from E to E, defined by P goes to NP, is a rational map. Right? Just taking a point and adding it to itself, this NP, remind you, is like P plus P n times. And taking a point and adding it to itself n times, I mean, just you can think of it, you can, I mean, prove this claim of the example inductively. So what really matters is that I take a point and let's say I add it to itself. So adding it to itself, this requires to solve some equations. I mean, I draw the line and I intersect the line with the curve, and then I negate the y coordinate. But all of this, I mean, I will not write the formula, although you can find it in the notes and in other places. But obviously, all these formulas are just rational functions. I mean, mostly they are polynomials, but when we do P plus P, we need to take the tangent line to P. And the tangent line has a numerator, right? So I actually get a rational function and not just a polynomial in each coordinate. Is this clear? Lisa, do you follow? Now, Nicolas?
Yes.
Now, what do you think?
Yes, it's clear. Thanks.
It's clear? Okay.
Thank you.
Okay, so now this is a very important map, right? Because we would like to understand. We would like to understand, for example, all the points that satisfy NP is equal to 0. this is a generalization. I mean, we have seen how useful was to understand exactly what are the points of order 2. And we also saw in the proof of Abel-Jacobi in the classification of divisors of line that we needed to understand some points of order 3. And in general, in order to really have a systematic treatment, we want to understand points of order n, or what is called n torsion points. So let's say the goal, understand what is called n torsion points. These are the points on E and here I take the algebraic closure of K. So this is the n torsion points are denoted E bracket n, and they consist of all the points in E over the algebraic closure, such that NP is equal to the point at infinity. So let's say this is one of the goals. One of the goals of talking about rational maps is to understand n torsion points. And n torsion points, they are basically it's like the kernel of the multiplication by n map that goes from E of K bar to E of K bar. Okay, so note that I can view a rational map, this mark, if a row from, let's say, from E to E is a rational map, and let's say E is defined over some field K, then for any extension L of K, I can talk about a function. I guess you can add a subscript L from E of L to E of L. Right? Because a row is, I mean, row is some pair of rational functions, R and S. R and S are defined over K. If they are defined over K, I mean, their coefficients are in K, then you can view them as rational functions over L, because L is bigger than K. And so you have the same thing. I mean, R of, sorry, this equation S of P So for any P now in E of L, I can do S of, I mean, I know that S of P square hang on, I don't want to confuse you. Okay, so I would have okay. Let me erase this remark. This there is a problem here. I mean, if I have a rational, okay, I'll explain. If I have a rational function defined over K, then I cannot necessarily extend it to a map between E of L and E of L prime, because if I have a point in E of L, its coordinates may not lie in K, and then I don't know that I don't know that this equation R P Q plus AX, sorry, plus ARP plus B. I don't know that this equation is satisfied because the coordinates of P may lie outside of K, and then I am not guaranteed any of this. So often when we talk about rational maps, we want that the rational map will be, even if E is defined over a non-algebraically closed field, we want that the rational map will be valid for every, I mean, will be defined over the algebraic closure. So I'll amend this remark. We usually want that for any point in E over K bar, the equation SP cubed is equal to SP square equals to RP cube plus ARP plus B will be satisfied. And if I have this property, I mean, if I have let's call it double star. A double star is usually the property you want from rational maps. And once I have double star, then for any L that is an extension field of K, this equation will be true. So I get a map rho from E of L. Okay. I'm sorry for the confusion. Maybe maybe you have questions on that. I can further clarify. So if you want, I will simply amend the definition. The remark is maybe amending the definition of a rational map so that for this equation, a double star, needs to be true for all points over the algebraic closure, not just over K. And once you have this, I mean, then you can regard the multiplication by n map, this bracket n, as a rational map. I mean, obviously, you take, you add 2 points over the algebraic closure over, I mean, 2 points of E over any field. You can define the addition of 2 points by quotients of polynomials. I mean, by rational functions. So multiplication by n map is a rational map. And the kernel of a rational map, I mean, is simply all the points that go to 0, to the point at infinity. So eventually, the n torsion points will be the kernel of a rational map. So if we understand rational maps, we have a good chance of understanding torsion points. This is kind of a glimpse to the future of why we are interested in such things. Maybe it's a lot to take. So, Lisa, what do you think?
Do I understand it correct that what you were trying to tell is that the map will hold for K only if it holds for the algebraic closure for K?
No, I want to say that, so let me just correct the definition.
Sorry, I had the feeling that I'm following, but then when you started to remove part of the explanation, I'm not sure.
Yeah. Okay. So let me just I'll correct the definition. This is something I should have done.
Oh, you mean we now are dealing only with algebraic closure of K and not with K on its own?
Yeah, although the elliptic curve may be defined over a non-algebraically closed field, but
Okay.
the rational functions that we consider will be always over the algebraic closure. And
because we want to make sure that they are well defined.
Because we want the rational functions to induce maps from E of L to E of L for any L between, I mean, for any extension of K.
Mm-hmm.
That is, we need this equation to be satisfied for any extent, for any extension L of K. But if this equation needs to be satisfied for any extension, it means that R and S need to be defined over the biggest extension of K, which is the algebraic closure. Because a point in P of L, sorry, in E of L, I mean a point P in E of L may have coordinates that are outside of K. So if the equation star is only satisfied for points with coordinates in K, we do not know that it is satisfied for points in E of L.
Yeah, that makes sense.
Okay, so what we really want is that the equation star will be satisfied for points with coordinates in potentially in K bar. And then we get an actual function from the L rational points to the L rational points for any extension L of K. Okay. So this I think this may be a good clarification. This is the content of the remark. And so, okay, so we have this example of a rational map. We have another more general example. Let E over K be an elliptic curve, and let's say Q is a point in E over K bar. Then the map I call it tau Q. Tau Q from E to E, defined by tau Q of a given P is P plus Q. So tau is like a translation. It's a translation by Q. So for any P in E of K bar, in particular, P could be, I mean, P could be in E of L for L, some intermediate extension of K. I mean, when I say P in E of K bar, this is the most general situation. And this is a rational map again. Okay, so this is again the formulas of addition of points on E. It tells you that translation by a fixed point is a rational map. Now, what do you think? Do you follow?
Yes.
Okay. So you understand this modification we did to the definition? I mean the K bar?
Yes, I think so.
Okay. So okay, so now we have a notion of how to move between elliptic curves, and if I'm about to move between elliptic curves, then I want to be able to compose two rational maps and still get a rational map. This is the next proposition. Let E over K be an elliptic curve, and rho and tau two rational maps. Rational maps can be composed, and I claim that let's say a tau composed rho from E to E is a rational map. I didn't exactly define how to compose rational maps, but I will do it in the proof. It's going to be very easy. You just substitute. So let's say that rho is r comma s, and tau is u comma v. And again, I remind you with our amended the definition of rational maps. I assume that RS, U, and V are rational functions over K bar. Then how do you compose? You take tau compose rho applied on some, it can be either a finite point or let's say a finite point. So it has two coordinates, x and y. And you do u of r x y. Or you know what? Let me do it straight on the level of points. So for any p in E over K bar, tau compose rho of P is you take R of P, S of P, and you plug it in into U. And in the second coordinate, you do the same thing for V. So you take R of P, S of P, and you plug it into V. This is, by definition, this is composition. And you need to remember that these guys may take the value of infinity at some point, but if one of them takes the value of infinity, then the other one, and then the two coordinates, if the two coordinates are infinity comma infinity, we interpret it as O, right? We assume that R of P, S of P, like this, is simply the point at infinity. Okay, and then everything is defined. I mean, I can always evaluate a rational function, say u or v, at the point at infinity. Or instead of assuming what we mean. Okay, so this is composition. I basically I didn't prove anything. I just wrote what is the definition of composition. But this is a pair of rational functions. I mean, I have a rational function in each coordinate. One rational function is you take P and you take the evaluation U of R of P comma S of P. This this guy, I mean, in this coordinate is simply a rational function from E of k bar, say, into P1. And also the second coordinate is a rational function from E. I mean, this is because I substitute. I mean, what is a rational function is just a quotient of polynomials. You substitute quotient of polynomials into a quotient of polynomials, you get a quotient of polynomials. Okay, so this is a pair of rational functions. And now I need to check that they satisfy the equation of E. I mean, we need to check. Let me denote these guys as what we have: RS, UV, and let's say AB. So we want to check that B squared equals A. Maybe I write it with P. This is A of P. This is B of P. And we want to check that B of P square is equal to A of P cube plus A of P plus B. But we know that R of P, that we know that rho is a rational function from E to E. So rho of P, which is R of P, S of P, is always, it's guaranteed to be a point on E. So, and this is rho of P, right? And also this guy is, I mean, in the other argument, I also have rho of P. So, and we also know that tau from E to E is a rational map, i.e., for any Q, tau is U comma V. So for any Q, U Q V Q is guaranteed to be a point on E. So take Q equals rho of P, then we get that A of P comma B of P is the point we want to check that is on E is guaranteed. This is simply sorry this is simply tau of rho of P, and which is tau of Q. Well, whatever. This is guaranteed to be a point in E. Okay, so this, I try to be very explicit here, but the content of the statement should be fairly intuitive, I would say. Any questions about the? Okay, now you're fine. Then let's just take a 10 minutes break. Unless Anna, you wanted to say something?
It was me.
Elisa?
Question. Yeah. We have like somewhere upwards the statement that if S over point of infinity is infinity, it implies that R over point of infinity is also infinity, and vice versa. I'm not sure I understand why.
This you can, because this equation cannot be, I mean, let's say if you take this equation, yeah, yeah, if one of them is infinity, then you cannot have this equation satisfied if the other one is not infinity.
Yeah, of course, it makes sense.
Okay.
But only for this equation, it's not for all rational functions.
No, only for this equation. So
okay.
It's a condition that we further require from the rational functions R and S. I mean, hypothetically, you can find, and not just hypothetically, I mean, also in practice, you can find rational functions R and S in which, for which, there is a point P such that R of P is infinity and S of P is not infinity. And for all other, I mean, but this equation may be satisfied for all other cases. This pair of functions will not be a rational function according to our definition.
Okay,
I mean,
okay, I got it.
Okay. All right. So let's meet again in 10 minutes. Okay. Let's start again. Now that we know that the composition of rational functions is a rational function, we can move a bit better between elliptic curves. I mean, imagine you can take the doubling of a point, say we can write it as a bracket 2. This is from E to E, and it maps P in E over K bar into a 2P. And I can, if n is even, then bracket n is simply a composition of two. Actually, I don't need n to be. Yeah, if n is even, then this is a composition of a doubling of a point. Let's say k times. So the next proposition may be a bit surprising, and maybe not so much if you think of it, because, well, let me just state it. So let E over K be an elliptic curve. And rho, which is R comma S, is a rational function, a rational map between E to itself. And here, okay, so if rho is not constant, it induces a surjective map between E over K bar to itself. Okay, so this proposition tells you that rational maps are rigid. I mean, you cannot have non-surjective maps that are defined by rational functions R and S. So, yeah.
Does surjective in this context means that it is surjective or bijective, or it is strictly surjective?
No, just surjective. It can certainly be not injective. Surjective means that for any point Q here, there exists some point P here, such that P is mapped into well, P is always mapped into rho of P, and I mean, for any Q, there exists a P such that rho of P is equal to Q.
Yeah, but why? I'm not sure I understand why it can't be injective.
No, it could be injective, but it could also not be injective. What the proposition guarantees that it's always surjective.
Oh, okay. And it doesn't tell us anything about injectivity or...
No, this you cannot guarantee. Why? You will soon see why. Okay. I mean, the answer to why is the proof, really. Okay. So let's first let's show the analogous statement for irrational functions say again rho from E to P1. So if okay, so maybe instead of rho, I do it for R. That is, R is simply a rational function over K bar. So if R is not constant, then it must have a zero. A zero over E of K bar. And what is the reason? Why does a non-constant rational function must have a zero?
Because it's a polynomial, and polynomial always has a root.
It will be either, yeah, I mean, it will be a quotient of polynomials, and polynomials always, they have to have a root because they have a pole at the point at infinity, right? So essentially, it must have a zero because of Abel-Jacobi. I mean, the numerator of, the numerator of R is a polynomial. This polynomial must have a zero by Abel-Jacobi, or some similar statement. For a point in K bar, the same argument, well, the rational function R minus x0, again, going from E to the projective line, must have a zero. But if r minus x0 has a 0, so say P is in the set of zeros of r minus x0, then r of P is equal to x0. I can write it a bit more detailed. R minus x0 evaluated at P. This is by definition R of P minus x0. This is equal to 0. This is the same as saying that R of P is equal to x0. So this R is surjective. It's surjective on the projective line. Of course, R, if it has a 0, it must have a pole, because so R is surjective. Well, so R let's say is surjective on K bar, but since R has a 0, it must have a pole again. This is Abel-Jacobi. And i.e., there exists some Q in E over K bar such that R of Q is equal to infinity. And this means really that R from E of K bar into the projective line over K bar is surjective. Is this clear? This is the main part of the proof, actually. Now, what do you think?
I'm processing. Digesting the. But so when I watch your explanation, it seems match and makes sense in my mind. But when giving a second read is when I find out that it's not so clear.
Let me just go over the argument again. At the moment, I just want to show that a rational function R on E over K bar is if it's not constant, it must be surjective. Okay? So I'm saying if R is not constant, then it must have a 0. Why does it have to have a 0? Because if it is not constant, then it is a quotient of polynomials, right?
Yes.
Yes. And the numerator of the quotient of polynomials, the polynomial at the top, it must, I mean, the polynomial at the top, if it's okay, so the polynomial at the top, let's say it's not constant, then it must have a 0, right?
I think I'm not seeing this part, I think.
Okay, so I'm saying if it's not constant, it must have a 0. This is basically the content of Abel-Jacobi. You cannot, I mean, you have to have the number of zeros with multiplicity has to be equal to the number of poles with multiplicity. So it has to have now a polynomial. A polynomial always has a pole at the point at infinity, right? Because if you substitute infinity comma infinity in a two-variable polynomial, you get infinity.
Okay, I see now. Thanks.
Okay, so I mean, you know that a polynomial, every polynomial that is not constant has to have a 0. This by Abel-Jacobi. And similarly, every non-constant rational function has to have a 0. Now, if every non-constant rational function has to have a 0, it means also that I take any x0 in k bar, and I take r minus x0. This is a non-constant rational function, right? It has to have a 0. But what does it mean that it has a 0? It means that this equation star is satisfied. This equation star is the same as saying that, I mean, it's satisfied for some p, right? Okay, so it means that I can reach every x0 by some point p. And so now I almost proved surjectivity, but I need to show that I also get the I mean, P1, I remind you, is like K union infinity. So I need to show that I also get infinity. But that's not a problem, because if R has a 0, it has to have a pole. This is the symmetry of Abel-Jacobi gives us all this information. So and what is a pole of R? A pole of R is some point Q such that R of Q is equal to infinity. So I get that R covers the projective line completely.
Thank you very much.
Okay, so this is for rational function, and now I want to prove the statement for rational maps. So and now consider rho is this R comma S. This goes from E to E. So if R is constant, then since for any P in E over K bar, we have to have S of P squared equals R of P cubed plus A R of P plus B. We get that S of P can take at most 2 values. Namely, plus minus square root of R P cube plus ARP plus B. I mean, remember, R is, I mean, if R is constant, then R of P is equal to R of Q for any P and Q. So this expression is constant since R is constant, and S has to satisfy. I mean, we have to satisfy this this equation star. So it means that S can take at most 2 values, namely the plus or minus of the square root of this constant expression. Okay, so but of course, if S can take at most 2 values, so S from E of K bar into P1 of K bar cannot be surjective. Right? Because the projective line over K bar is always infinite. And if S can take at most 2 values, it cannot cover an infinite set. So by the above, S must be constant. Okay, so what we proved here is that if R is constant, then automatically S must be constant. And if R and S, I mean, if R and S are constants, then rho itself is constant. Otherwise, R must be surjective. If it is surjective, it has a pole. Hence, it has a 0. Or, you know, you could go the other way as well. If it's surjective, it has to have a 0, and hence it has to have a pole. In particular, there exists a P in E over K bar such that R of P is equal to infinity. In this case, it follows that S of P must be infinity as well, right? This is the defining property of rational functions, rational maps, is that if one of the coordinates, one of the coordinated functions, either R or S, is infinity at some point, then the other one must be infinity. And this means that rho evaluated at P, which is R of P, S of P, is simply the point at infinity. Okay, so let Q be an arbitrary point in E over K bar. Then translation by minus Q is a rational map from E to itself. And thus, you take translation by minus Q and you compose it with rho. Composition, rho is a rational map. Translation by minus Q is also a rational map. So the composition is also a rational map. It is a non-constant tau minus Q compose rho is non-constant. Hence, it has a pole. There is some P prime in E over K bar, such that tau minus Q composed with rho evaluated at P prime is the point at infinity. But then, what is tau minus Q composed with rho? It means that minus Q plus rho of P prime is equal to O, which is the same as saying that rho of P prime is equal to minus 2Q. So rho from E of K bar into E of K bar is surjective. Okay, I took an arbitrary point Q in E over K bar, and I have found a P prime that satisfy this box equation, that is a point P prime such that rho of P prime is equal to Q. So I proved the surjectivity. Lisa, what do you think?
I think I need time.
Okay, it's fair enough, but I can also repeat the argument.
Yes, please.
Okay, so let me ask this. Do you understand the first part? The first part?
Yes.
Arnaud, do you understand the first part of the proof?
I think, yeah.
Yeah, so the first part is just saying, I mean, every rational function on E is either constant or surjective. Okay?
Right.
Now we move to the general claim. So the general claim, here starts the general claim. I consider a rational map. It has two coordinates, R and S. Now I look at the first coordinate R, and I claim that if the first coordinate is constant, then the second must be constant as well.
Yeah, that's clear.
This is clear, right? Because I need to satisfy this equation star all the time. I mean, if this equation in the right-hand side is always a constant expression, R of P is always constant, then also the right-hand side, the left-hand side must be constant. So if rho is constant, it really means that I mean it's enough for R to be constant to deduce that that rho is immediately constant as a function. So I mean, or if you want, we can. I mean, in the general case, we consider rho, which has two coordinates, R and S, and there could only be two cases. Either the first coordinate of rho is constant, and this automatically implies the second is constant, or the first coordinate of rho, namely R, is not constant. But if it is not constant, then the first part of the proof show that it is surjective. Okay, so in fact, if I know that rho is not constant, then I know that R is surjective. Okay.
Okay.
So if it is surjective, it has to have a pole and a zero, because I mean surjective means that there is some point Q such that R of Q is infinity. Remember, surjective means surjective on the projective line. Right? So it means that there is a point Q such that R of Q is infinity, and there is a point Q prime such that R of Q prime is zero. Is this clear?
Yes.
Okay, so this is what is said here. It has to have a pole and a zero. Now, are you with me?
Yes.
Okay, so I take a pole of R. Let's call it P. So P is a point in E of K bar such that R of P is equal to infinity. Okay, but since rho is a rational map. If R of P is equal to infinity, then also S of P is equal to infinity.
Right.
But if R of P is infinity and S of P is infinity, it means that rho of P is O.
Right.
Right? Okay, so I have found a point P which is such that rho maps P to the point at infinity. Now I take an arbitrary point Q in E of K bar, and I want to find some P prime that is mapped by rho into Q. If I can find such a P prime, I finish my claim, because I want to show surjectivity of rho.
Okay.
You with me or no?
Yes, yes, yes.
Okay, so I took an arbitrary point Q, and I consider now the translation by Q, by minus Q. Translation by minus Q, it takes an arbitrary point, I don't know, T, and it maps it to T minus Q. Right?
Okay.
And this is a rational map. This was one of the examples. Because adding or subtracting points on an elliptic curve, you can do it with a quotient of polynomials. Is this clear?
Yes.
Now? Okay.
Yes.
So this is a rational map. If it is a rational map, I can compose it with another rational map. So I have, this is translation by minus Q. And I also have rho. And I can compose, I can compose these two rational maps to get here translation by minus Q composed with rho. This composition, this is what we talked about we had a proposition about it, you remember?
Yes.
So composition of rational function, of rational maps, is again a rational map. Now this rational map cannot be constant. If it was constant, then rho was constant, right? Because this rational map is just in formula, you take P and you map it into rho of P minus Q. If this is constant, then it means that rho is constant.
Right.
Okay, so since I know, I assume that rho is not constant, then this map is also not constant.
Oh, and if it is not constant, it should have 0. It must have 0, so it has there is a point.
Yes, this is what we proved. I mean, we proved that every non-constant rho, we proved it on rho, but this is true for any non-constant rational function, has to have a point that maps to O. Right? The way we proved it, we said if it is not constant, then the first coordinate of it is not constant. I mean, the first coordinate R is not constant. Hence, it is surjective as a rational function. Hence, it gets a point. It has a point that maps to infinity. But then S has to map this point also to infinity. So altogether, rho would map this point into infinity, comma infinity, which is O. So the takeaway from this part is that every non-constant rational map has to have a point that maps to O.
Yes.
Now you with me? Okay.
Yes.
So in particular, also this rational map, translation by minus q composed with rho, has to have a point P prime that maps to O. Right?
Right.
But this is simply saying that a rho of P prime minus q is equal to O, which is the same as saying that a rho of P prime is equal to q.
Okay.
Okay, so I get that rho is surjective. I chose q. I didn't have any restriction on q. Q was arbitrary. And I have found a point P prime such that rho of P prime is q. Okay, last questions before we end up.
Thank you for this recap, like this repetition.
Sure. Just feel free in every session to ask for repetition, and I'm happy to make it.
This is a very optimistic session because it feels more, much more clear than the last 3 or 4 that we had before.
Okay, I'm glad and also a bit sad that the previous ones were not as good, but
no, it's just this one is composed of kind of like parts that are familiar and clear, and that's why it is easier.
Yeah, it should be easier. It is definitely meant to be easier. As I said, the Abel-Jacobi is the biggest result that we have proved so far. So it's natural that it's more complicated to understand. And again, I'm happy to revise it at any point if you want, even next session. But you can also read it in the notes, and
Yeah.
I think, yeah. I mean, as you wish. So just you can ask me at any time to repeat. Okay, so that's it for today, and have a nice weekend.
Thank you.
Thank you very much.
Bye.
Bye.